it's so we're using the exact uh, solution of the differential equation. It's sort of the same steps. Um, it's already in the standard form. So this here is our m, and this here is our n. What multiplies the derivative is n. The other one is the m. Okay. And now we check to see if it's exact. And we know if it's exact, that's if and only if dm over dy has to equal dn over dx, partial of n with respect to x. So let's find out what dm over dy is. So we differentiate with respect to y, holding x constant. So the first one will just be secant squared x plus 0, because secant x, tan x are functions of x. So when we differentiate with respect to x, with respect to y, there's zeros. And then dn over dx will be tan x, will just be secant squared x, and 2y, we hold the y fixed, so y is not the variable now. So plus 0. And indeed, they are the same. Therefore, it's exact. And if it is exact, then there exists some function potential whose gradient are the m's and the n's. So that means there exists some f whose partial with respect to x has to equal m. That means df over dx has to equal y secant squared x plus secant x tan x. And now I could just move the dx over here and integrate all sides, both sides. So of course the left hand side will get me, let's go back to the original. So that means if we can continue here in blue, that means f of x comma y. Now we can separate the integral, and we're integrating with respect to x, so y is constant. So the integral of secant squared will be tan, so y tan x, and secant tan will be obviously secant plus secant x plus constant of integration in this case will be some function h of y. And I also know that partial of y has to equal n. So partial of f with respect to y, I can differentiate the above expression. So the derivative of y tan x, I hold the x fixed constant, I differentiate with respect to y. So we get tan x. Derivative of secant is 0. And this is just h prime of y. And this in turn has to equal the n, which is tan x plus 2y. Therefore, tan x plus h prime of y has to equal tan x, n is tan x plus 2y. Goes away, and we get h prime is just dh over dy is equal to 2y. And likewise, we can just move the dy here, and we can integrate both sides, and we can get h of y to be y squared. And we can substitute that in the in f right here, star. So substitute in star. So then we get f of x comma y fully characterized as y tan x plus secant x plus y squared, which means we have a family of solutions of y tan x plus secant x plus y squared equals c.
Was the derivative of secant squared to negative 2 tangent?
You mean the integral or the derivative?
Derivative.
Do you need that?
Yeah, I was trying to find it.
Where did you notice that you need that?
The first for the Oh no, wait, I don't need that.
You don't need that. You need to integrate secant squared, not differentiate it.
Right.
Okay, so now we're at the point where we can use the initial conditions of the problem to find c. So y of 0, let's use another color on this. Y of 0 is equal to 1, I believe. So that means when x equals 0, y equals 1. So we're going to plug it in, and we get tan 0 is 0, so 0. Secant 0 is 1, plus 1 equals c. So c will equal 2, because this guy is 1. So then we're going to plug in c here, and we will get the general solution of our differential equation to be y tan x plus secant x plus y squared equals 2. And this concludes the problem, where now we singled out the curve, very specific curve out of an infinite amount of curves that satisfy the first order differential equation.